All right, today we're cracking open the black box. We're going to take a deep dive into a really cool tool called Centered Kernel Alignment, or CKA for short. It's a method that helps us answer a question that's been bugging AI researchers for years.
You hear it all the time, right? Neural networks are a black box. So let's say you train two different AI models to do the exact same thing. They both work great, but did they learn the same stuff? Are their internal thoughts, their representations, anything alike? That's the huge question we are tackling today.
So, the first thing you might think to do is just grab cosine similarity. It's super intuitive. You take an internal piece of data from one network, a piece from the other, and you just see if the vectors are pointing in the same direction. High similarity if they are, low if they aren't. Simple, right? Yeah, maybe a little too simple. And that really gets to the heart of the problem. Cosine similarity is just a pairwise local view. It's a quick fix, kind of like a Jew-God solution. What we actually need is something that can see the whole picture. We need to understand the structural alignment, the pura ka pura structure of how the AI is thinking, not just compare one thought at a time. And here's why that pairwise view is so flawed. I mean, what if one AI's entire representation is just a rotated version of the others? Cosine similarity would just fall apart. It can't tell you if the relationships between all the data points are the same. It's a local measure, and it completely misses the global geometry of the knowledge. So to fix this, we need a better tool. And that brings us to our first building block, the Gram matrix. This is how we're going to capture that entire relationship structure we've been talking about.
Okay, so what is a Gram matrix? Well, just picture a big grid. Every single cell in that grid tells you the similarity, usually just a simple dot product, between two different data points. So the cell at row 5, column 10, tells you how similar data point 5 is to data point 10. Suddenly, you've got a complete map of all the internal relationships in one shot.
The best way to think about it is this. Instead of going around and checking friendships one by one, you're creating a complete social map of an entire town. You see everything at once, who the friend groups are, who the loners are, all of it. That's what a Gram matrix does for our data. All right, so now we have these relationship maps from our two AIs. So how do we compare the maps themselves? Well, for that, we need building block number 2. This is the engine that's going to power the whole thing, and it involves a funky-sounding thing called HSIC, and the absolutely crucial step of centering. So the engine is called the Hilbert-Schmidt Independence Criterion, or HSIC. It's basically a fancy statistical test that asks a really simple question. If the similarity between 2 points goes up in network A's map, does it also go up in network B's map? It's all about measuring if those two relationship maps are moving in sync. And the takeaway here is super simple. If HSIC spits out a 0, it means the two structures have nothing to do with each other. They're independent. But a high score, that means they're strongly related, that the patterns of relationships are really similar. And that is exactly what we're looking for. But wait, there's a catch. Of course there's a catch. What if one of our maps is, just shifted over a bit? Maybe one network has some kind of bias that pushes all of its data points in one direction. The internal structure, the relationships, could be identical, but because they're not lined up at the same starting point, a simple comparison would totally fail. The solution is just so elegant. It's centering. You basically tell the algorithm, "Subkuch center align kar do." You just mathematically shift both of these maps so their average is right at the origin. This gets rid of any weird bias and forces the comparison to look at the pure internal relational structure. It's brilliant. And believe it or not, the math for this is surprisingly simple. We use what's called a centering matrix, which we just call H. You can see the formula here. It just takes the identity matrix and subtracts the average. And when you multiply your Gram matrix K by H on both sides, poof, it just subtracts the mean, giving you a new, perfectly centered matrix that's all about those internal relationships. So let's recap. We have our relationship maps, the Gram matrices, we have our comparison engine, HSIC, and we have our alignment tool, centering. When you put all of that together, you get the payoff. You get CKA. The whole process is really just a clean 5-step pipeline. First, you grab your raw representations from the AI layers. Then you compute those Gram matrices. Step 3, you sitter them with that H matrix. 4, you calculate the HSIC between your two now centered matrices. And finally, you normalize the scores so you get a nice clean number between 0 and 1. And that right there gives us the full formula for centered kernel alignment. I know it might look a bit scary at first, but now you understand every single piece.
right? It's just the HSIC of our two centered Gram matrices divided by a normalization factor. We literally built this thing from the ground up.
So, okay, that's the theory. But what does CKA actually show us that the simple stuff misses? It's time to see the results. Let's look at the OSLI picture and see why this is all so worth it.
Okay, check this out. This is a similarity heat map between the layers of two different networks. This was calculated using another method called canonical correlation analysis, or CCA. And, well, you can see, it's a mess. It's noisy, it's blurry, it's almost impossible to tell what's going on. You'd probably conclude the networks learned totally different things.
Now, look at this. This is the exact same comparison on the exact same networks, but this time using CKA. The difference is absolutely night and day. We see this beautiful, sharp diagonal line. What is that telling us? It's showing that layer 1 in the first network corresponds perfectly to layer 1 in the second, layer 2 to layer 2, and all the way down. CKA found this deep similarity that CCA just completely missed.
And when you look at the actual CKA score for those matching layers, you get numbers that are just ridiculously high, like 0.9998. That's not just a pretty picture, it's hard, quantitative proof that even though they started randomly, the two AIs learned almost identical internal structures. The hidden geometry of what they know is basically the same.
Now, CSK is obviously incredibly powerful, but no tool is perfect. So before we finish up, let's just quickly cover the fine print, its biggest strengths, and the gotchas you gotta watch out for. So the pros are massive. It doesn't care about rotation, it captures that global structure we wanted so badly, and it's amazing at matching up layers. The downsides? Well, calculating those huge Gram matrices can be computationally expensive, and your final score can be a little sensitive to the exact similarity function or kernel that you choose to use at the very beginning. And really, this quote from the original paper just sums up the entire idea perfectly. The big philosophical shift here is to stop comparing the AI's thoughts directly. Instead, you first map out the entire similarity structure within each AI's mind, and then you compare those structures. And that really leaves us with a pretty mind-bending final thought. Now that we have a reliable way to peek inside that black box, a way to actually compare what different AIs have learned, what's the next big question we should ask them? What mysteries of intelligence are we now ready to start solving?